Alright, so today we're going to be talking about Dijkstra's algorithm. Now, this is an algorithm we've sort of seen before, but could use a bit more explanation and a bit more of a run-through. It's an algorithm to find the shortest path. Now, when we think about shortest path, we're trying to think, well, what does that mean in a graph sense? It means, well, the minimum distance, minimum value of distance from one node to another node. And as you might assume, this has tons and tons of important applications all across the world. We're always looking for, all right, how do we get from A to B in the fastest amount of time, in the shortest path? How do we traverse this with the least amount of resistance? Yeah, well, Dijkstra's algorithm is going to help us out a lot because in the end, it's relatively efficient and it shows us a few things about graphs, not just the shortest path. Take a look at this example here, and you're going to notice a few things right off the bat. For one, the graph on the left has 4 nodes, A, B, C, and D, and every edge has a number associated with it. And I know it's a little sloppy, but that's just my finger drawing ability here. But you should be able to see that, say, the edge from A to B is going to be 3 as far as its value. Now, we haven't defined it as a distance yet, but we're just going to assume that, yeah, sure, that's the distance. And if you look closely, you might say, well, it doesn't make sense because it doesn't look like A to B is 3 and A to C is 6. They're about the same distance. Well, we can't assume that our graphs are drawn to scale. One thing we know about graphs is we can have 2 versions of the same graph, but drawn very, very differently. So never assume anything about the graph and its distances. Okay, on the right we have this table, and I've marked the first column and the second column with a whole bunch of different nodes, and then the third column is all 99s. And you're going to be like, okay, what's going on here? So part of Dijkstra's algorithm, we want to set up this table of values, and it's really a table of distances or of shortest distances between the first column node and the second column node. So for example, at the top, where we've got A and B here, the shortest path from A to B right now is 99. Like it takes 99 to get from A to B. And you might think, well, that's not just true, that's false. And you're right, well, but we have yet to calculate it. So we're going to change this value. Every single 99 is going to be sort of replaced, and well, can't erase just yet, so maybe I'll write over it in a second. Okay. Alright, it's important to keep track of these values because they could change. And then the final thing that we're going to do is we're going to sort of give ourselves a bit of a color code right here. So we'll use a black mark, we'll keep it as is, to tell if a node is what's called unvisited. And a green mark on our node to say that it is visited. And this is going to be important because once a node is visited, we don't need to visit it again. We only need to visit every node just once. Now, it's not the same as checking it or seeing it, because in order to visit a node, you need to have seen every single path to it, essentially every edge that connects it. So we're going to start with A in this algorithm. We'll start right here. And what we're going to do is we're going to calculate the distance from A to each of its neighbors. Now, that's relatively easy because we can just write down the number associated with it, and yeah, in the end, Dijkstra's algorithm is just a bunch of writing down numbers. So we're going to say, alright, well, for A, we have this edge to B, which has a distance of 3. So I'm going to go ahead and kind of cross this out here. I'm going to write a 3 right below it. I normally would erase, but the software is not allowing me to. A to C, right here, is not 99. It is 6. And A to D is not 99. It is 4. Now, right now, you might be asking, okay, well, why did we even have 99 to begin with? Well, the point of that is we need a place to set it, a value to set it at to begin with, since the way in which we overwrite our distances is if there is a minimum if there is a new minimum distance, right? Because we're trying to find a shortest path. So this is very similar to finding, say, a minimum or a maximum within a set or a collection, a list of numbers. And we've done that before when trying to sort, right? When we did selection sort, we were selecting the minimum from the list and moving it down. Well, now we need to find the minimum, but each time to find the minimum, we need to reset our new current minimum and compare it with the one we're looking at. Okay. All right. So we've done that. We've checked A to every single one of its neighbors, and once we've done that, we can say, you know what? We've seen all that A has to offer. It is now visited. All right. So once it is visited, now we need to move on to a new node that is unvisited, and it's going to be a neighbor of A. So let's say we move on to this new node, B, and currently we have already B to A as a distance checked, but we need to check, say, a new distance, B to C here. So B to C is going to be the value here of 2. And some of you might be noticing something right now, that we also have created a path from A to B to C. Now the reason why we care about this path and what B and C is in reality, Dijkstra's algorithm, we are only actually checking for the shortest path of A to every other node. So these values here are kind of like placeholders. They're not our answer in the end, but they're going to help us update the first 3 values, the first 3 distances, A to B, A to C, and A to D. The reason for that is we just checked B to C, and what we need to compare is if B to C plus A to B, I'm going to write that down, if BC plus AB is greater than, or in this case less than, AC. Because we want to see if that actually is a shorter path than A to C. And in the end, it is. So what we have here, and I'll check it in blue, is B to C we found was 2. And if we add that with the 3 from A to B, that gives us 5, which is less than our A to C value. Let's see if I can erase here. Cool. So we now can update. Oh, that's a highlighter. This value to be 5. Cool. And once we've updated it, well, guess what? We saw every node that B is associated with. We're done with B. And we can continue on with C now. And really, we've checked C and B. We've checked A and C. We have those values already updated. The only one we don't have is this one down here, C and D. And so we find that that is 5. Okay, but why does that matter? Well, with C and D, we now have to see if, well, C to D plus B to C plus A to B is less than A to D. So we've created this really long path, here, 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 all the way to D, and we want to see, is that shorter than the path here? Now, we know right now, just by looking at that, by doing a little bit of that math, that's not the case. But we do need to compare that in this algorithm. Now, the first value that we're going to sort of adjust before we compare is we're going to be adjusting B to D. The reason for that is similarly to the way we did A to C after we're looking at B. Well, we need to know that, all right, update B to D is actually 5, because that's what C to D was, plus C to B, which was 2. So our total of B to D is going to be 7. This allows us to find out what A to D is comparing or at least comparing or updating a to d, which is 4, to our new a to d that we're seeing right now, which is a to b plus this new b to d, which is 7. So we're always using these placeholders to reevaluate our shortest paths from a to any other node. Once we're done comparing and seeing that nothing needs to be updated, we'll say, you know what, C is actually visited, great. We'll move on to our last node, which is D, and it turns out that all of the edges that D has already been checked, and that's going to happen for any time we go to the last node. So we're going to say, you know what, that's visited. Now we come to sort of the end of the algorithm, and the end is, well, once every single node is visited, then you're done. What's our outcome? What's our result? Well, this is our result right here. This table of values for A to any other node, and it shows the shortest path from A to B, A to C, and A to D. Now, normally in Dijkstra's algorithm, we are just looking for the shortest path between two nodes, like A to C, for example. We're not just looking at the shortest path of every single A to whatever node, but Dijkstra's algorithm also checks that in addition to looking at the shortest path between A and C. So it kind of does more than just one thing, just through the nature of the algorithm and through the rigorous process. But traditionally, we're only looking at the shortest path between it and one other node. And you might assume or guess that in practice, in applications, well, we don't really care. Once we get the shortest path between A and C, and both A and C are visited, we don't really care about looking at any other values our graph has to offer, since that was sort of the result that we were looking for to begin with.